Anybody have any homework questions you'd like me to go over?
Number 2 of the most recent one.
Number 2. Okay, so we are on part 2 of control volumes.
Yep.
Okay, so we have a
Projectors and pods.
Oh, thank you. Okay, so we have a turbine. It's insulated. What does insulated tell us? Yeah, no heat transfer. At steady state, develops this much power, and it gives us a steam flow rate in, it gives us m dot. Tells us some information about, so it tells us the temperature and the speed at the inlet, and it exits as a saturated vapor with this stuff. Okay, neglecting potential energy. All right, so a turbine, any of those 5 device types, we know we're going to be using the differential form of the first law for control volumes. Okay, we're doing the control volume thing. Okay, so control volumes, part 2, number 2. And so we start out with this. d dt is equal to q dot for the control volume minus w dot for the control volume plus mi dot times the quantity hi plus vi squared over 2 plus gzi minus m exit dot times the quantity h exit plus v exit squared over 2 plus gz exit. And it's steady state, so that's 0. These are both just m dot. It's insulated, so that's 0. It gives us speeds, so we're not going to want to throw away the kinetic energy term. Wait, yes, it does, right? Neglect potential energy effects. So cancel those. And now we'll fill in the stuff that we know. So let's see, we got 0 is equal to the work done by the control volume is 23 times 10 to the 6th watts. The mass flow rate is 40 kilograms per second. And if I group this stuff all together, I can think of this as HI minus HE plus VI squared over 2 minus VE squared over 2. And we know those speeds. At the inlet, 35 meters per second. So plus 612.5. And then at the exit, it's 120 meters per second. So that's minus 7,200. Okay, well, we're getting close. We have two variables. So now we have to think about what we can calculate. We're told that steam enters at 360 degrees Celsius. We don't know that it's saturated or anything like that. So in general, you need two properties in order to look up anything about steam, okay, or to calculate anything using the ideal gas law. And so we can't look up or calculate anything right now at the inlet. But at the exit, it is a saturated vapor. And a saturated vapor, you can look stuff up given a single property. So we're going to go to the saturated vapor table and look up 0.06 bar, which I think is one of the little subtables in there. So we can just look it up directly. So let's go to the tables. And we have water at saturation. We know the pressure, so we're going to use the one that's indexed by pressure. Okay, so 0.06. And what we want is we want to look up the enthalpy at that pressure. So 0.06 go across to the enthalpy. And we want the saturated vapor. So that is 2567.4. That's in kilojoules. We're doing everything in SI units. So 2567.4 times 10 to the third. So minus 2567.4 times 10 to the third, plus 612.5, minus 7,200. And so 23 times 10 to the sixth is equal to 40 HI. Minus 1.0 296 times 10 to the, that is not right. What did I do? I multiplied something instead of 40. Oh yeah, that's right. And so plus 23 times 10 to the 6th divided by 40. Okay, so what we get from that is that at the inlet, the specific enthalpy is 314 3149 times 10 to the third. And this is in joules per kilogram. Okay, so now what we know at the inlet is that we have a temperature of 360 degrees Celsius. And the specific enthalpy is 3149 times 10 to the third joules per kilogram. Well, at the inlet, this is steam. So we can't use that saturation table for this. We want water vapor and 360. Okay, so we're looking for a specific enthalpy of 3149 at 360 degrees. $31.49, so it's a little less than this. $31.49. As the pressure goes up, you can see these enthalpy values going down a little bit. 360, 31.49, 38. Okay, so it's in between. So at 360 degrees Celsius, we're looking for 31.49. It's in between a pressure of 2 megapascals and 3 megapascals. Okay, see that? Okay, so how would you get it exactly? Well, we could do linear interpolation, where these are the two boundaries of our independent variables, okay, and calculate what that pressure is going to be. Pressure is the, let's do that. Okay, so at an enthalpy of 3138.7, I'll call that enthalpy 1. The corresponding pressure is 30 bar. And at a specific enthalpy of 360, 3159.3, This is H2. The pressure is 20 bar. So the pressure is equal to 30 plus 20 minus 30 divided by 3159.3 minus 3138.7 times 3149 minus 3138.7, and pressure is 25 bar. Which means that if you would have noticed that 3149 is exactly the midpoint of those two, then you would have known it was exactly the midpoint of the two pressures. I didn't notice that, so I went through the calculation.
Can we do number 4 as well?
Sure. Anybody have any questions about that one? Because all of our tables are in SI units, I don't think we have any in those units. Let me look at one thing real quick.
The U of M has like an available in 3 textbook.
Oh, yeah?
Fundamentals of Engineering.
Uh-huh.
Has the imperial tables, I believe.
Okay. Okay.
Just to be-
All right, so let's see. Ideal gas, saturated. Yeah, it looks like this is all Celsius and stuff. Okay, well, I can tell you roughly how to approach this, but I'm not going to go through all the unit conversions and stuff. So you have a pump that's lifting liquid water. Yes, a total distance of 40 feet. It tells you what kind of stuff to cancel. Okay, so if we start with this, is it steady state steadily? Yes. So I'm just going to write this as m dot. Steady, so this goes away. There's no heat transfer, so that goes away. We have a pressure and a temperature at the inlet. The volumetric flow rate. So the mass flow rate is equal to the density times the volumetric flow rate. You can usually get good results by assuming that the density of water is 1,000 kilograms per meter squared. It does vary a little bit with temperature, and so it gives you a temperature. So let's say we wanted to be as accurate as possible. Take that temperature to, so this isn't saturated, right? We don't know anything about whether it's saturated. But the density of water only depends on the temperature, okay? So go to the saturation tables where you can look stuff up by temperature, even though this isn't saturated, and find the specific volume of water at that temperature that's given, okay? So this is not at saturation. But use the saturation table for the specific volume at the given temperature. And then the density is 1 over that specific volume. It's going to be right around 1,000 though. Then that gives you your volumetric flow rate. You have the speeds, so you can enter those in there. This is where that height change is going to come into it. And so the last thing we need is the enthalpy. So at the inlet, we're given a pressure and a temperature. We could calculate the enthalpy there. If the thing is rising 40 feet, pressure times volume. So the enthalpy is equal to the specific internal energy plus PV. We can assume this is incompressible, so V isn't going to change. For an incompressible material, the specific internal energy only depends on temperature, remember? And so this isn't going to change. There's no reason to think the pressure is going to change. And so, we're just dropping this thing off 40 feet higher. We're pulling it out of the atmosphere and dropping it off in the atmosphere 40 feet higher. That's not a significant change in pressure due to altitude. And so we're just going to assume that enthalpy is equal to 0. The change in, not the enthalpy, but the change in enthalpy between the inlet and the exit. And based on that assumption, now you can calculate that work requirement. Okay?
Mhm.
Any questions about that? Okay.
Do you ever have to think about the enthalpy? It says like our standard assumption for pumps is delta H is 0. Can we always assume that?
Oh, well, don't always assume that. Start with the full equation, cancel out what the problem tells you to cancel, and then make reasonable assumptions in addition to that, so you get to the number of variables you need. That's how to think about that. Usually it's a reasonable assumption to neglect the speed change. There's no significant kinetic energy change or anything. But in this one, it gave us the speed, so we'll leave those in there, Okay. Well, let's go to, so we're done talking about control volumes for the first law. So let's do just sort of a thorough outline of the class so far, fit in the equations as they come up. So this is an outline of the class before we get into, heading into the second law of thermodynamics, which involves entropy. So first we started with sort of an introduction. We talked about pressure, and we had an equation for pressure that said if the fluid is continuous and at rest, the pressure at the lower point minus the pressure at the higher point is equal to the density of the fluid times the acceleration of gravity times the difference in heights. And we talked about barometers, and manometers. And then we brought up work. And there are 3 ways that work can come up. The first one is the work of expansion. When might you see work of expansion? What kind of materials, what state of matter are you going to see significant work of expansion? What? Yes, that's right. This is only gases or vapors. We don't deal with solids really at all in this class. Liquids we treat as incompressible almost all the time. So we're only going to do that with vapors, and the work is equal to the pressure, dV, from the starting volume to the ending volume. To compute this integral, what do you need? What information do you need? Well, what you need is pressure to be known as a function of the volume. Okay, so for example, a case like, where did I put this in here? We've seen this a lot in the form like PV to the R is equal to some constant. By the way, that's called a polytropic process, if you want to sound smart. But a relationship like this, if you have enough information to calculate the two constants in here, then you can turn that around, express pressure as a function of volume, and compute that integral. Okay? The easiest case for computing this integral is if you have constant pressure. And so my advice is, if you ever see a problem that says constant pressure, store a little message to yourself in the back of your mind that's like, I'll bet I'm going to compute that work integral. You know? Okay, what other kinds of work are there? Two other kinds of work. One is electric power. And you always have to think about the sign convention. So in the case of a pump, for example, the electric power is being provided to the system, by plugging it into the wall. If you're talking about a turbine, that electric power is being supplied by the system. Okay, so you have to think about that sign convention. And then the last one is rotating shafts. Then we talked about the first law of thermodynamics. And we started with closed systems. I guess the way I have that is this part 2 is just the first law of thermo for closed systems. We'll get to control volumes later. And that says the change in energy is equal to Q minus W. You always have to be aware of this sign convention. Positive Q means heat added to the system. Positive W means work done by the system. And you can always think of that as a piston where you're heating up the gas inside the cylinder, and the result is that the piston rises. So that's energy being added to the system through heat, and then work being done by the system on the surroundings as a result. And the definition of E is the change, or delta E, is the change in the kinetic energy plus the change in the potential energy plus the change in the internal energy. If a problem doesn't say anything about speed or anything about the height changing, it's reasonable to assume that we're only talking about internal energy. Okay? Okay, so the first thing is simplifications. There are two cases where the change in energy is equal to zero. The first one is if it says steady state. More often it talks about steady state using the differential form. But if the differential form has dE dt equal to zero, and then you think of that happening over some time, that also means that the change in energy is equal to zero. Okay. Another thing that we haven't seen in problems but can give you that same information is if it says that we're looking at this process over a cycle. A cycle means that you return to the same state you started at. And so that means the same thing in this case. Cycles are going to be a big thing in the second law. And then we talked about the differential form of the first law. And that says dE dt is equal to Q dot minus W dot. This is the rate at which energy enters the system through through heat. We still have that same sign convention, so that's why this has to be energy entering the system. And W dot is the rate at which energy leaves the system through work. What are some indicators that we're dealing with the differential form of the first law and not the full time interval form of the first law? The first one is anything given in watts. Okay, watts is energy per time. So this tells you that you're dealing with something on a per time basis. Okay, so look for if the values you're given are given in watts or kilowatts or anything like that, that probably means that you're going to use the differential form. Okay. Another thing to look for is a time dependence on anything. So let's say a time dependence on any of your variables. Every problem that we've done where something is given as like 5t or something for t in seconds or t in minutes or whatever, you're going to use the differential form for that, and you're going to have to probably integrate it. And then the third thing is if you're given any, if you're asked to do any heat transfer calculations. So I haven't gotten to those yet on this list, but remember we have equations for radiation, convection, conduction. If you're asked to do any of that stuff, you're almost certainly going to be using the first law with the differential form. And then simplifications. There's really only one important one here, and that's that dE dt. If it says steady state, then you know dE dt is equal to 0. Okay, so third, the heat transfer equations. The thing you have to remember with these is, you know, you do the calculations, you use these equations, your answer is either positive or negative. You can't trust that sign when you go to the first law. So remember, you can't trust the signs that come out of these equations in the first law. You have to give it a sign based on whether energy is entering or leaving the system. Okay? So you can't trust the signs of the heat transfer equations with the first law. Okay, so the heat transfer equations, we have conduction. That says that Q dot is equal to negative coefficient of thermal conduction times the cross-sectional area times dt dx. For us, you're always going to be able to just replace this by the difference equation. So that's the change in temperature over the change in thickness of whatever it's traveling through. Technically, you can only do that if you have a linear gradient of temperature as you go through the thickness of the material, but we're always going to have that. Later on, when you have a full class in heat transfer, then you'll deal with more complicated functions. Second is radiation. And for that, we have the Stefan-Boltzmann equation. And that says Q dot emitted is equal to the emissivity times the Stefan-Boltzmann constant times the surface area of the object times temperature to the fourth. And remember that to use this, this temperature has to be in an absolute temperature scale. So you can't use Celsius or Fahrenheit for that. Remember that this equation is not the net radiation. So this is not that useful in the first law. The only way that we can use radiation with the first law, okay, not so useful for the first law. To use radiation with the first law, the only case we can deal with is a smaller body totally enclosed in a larger body. So a smaller body surrounded by a larger body. And then Q dot emitted net. The key thing is this tells you how much is going in and how much is going out, instead of just 1/2 of what we need. This is equal to the emissivity times the Stefan-Boltzmann constant times the area of the smaller body times the quantity temperature of the body to the fourth minus the temperature of the surroundings to the fourth. And again, these have to be absolute because that's not a difference of temperatures, it's a difference of temperatures to the fourth power. And then the last one is convection. And the equation for convection says the rate of heat emitted is equal to this catch-all constant H that you have to determine experimentally times the area of the body, your system, that's exposed to the fluid that's carrying heat to or away, times the quantity temperature of the body minus temperature of the fluid. So this H is experimental. You have to figure that out for your specific application. And this A is the area that's exposed to the fluid. Any questions about any of this so far? Okay, we're about half done, I suppose, with this. So I'm going to stop here, and then we'll just keep going with it at the start of class next time. And then we'll get into the new material.
So